All right. Hi, everyone, and good evening from Boulder. It's past midnight here, but I'm very happy to be giving this talk live, given the number of participants that are in this call here. So, taking off from Javier's question on Gaussian anamorphosis, here we'll be taking a fresh new look at this approach to nonlinear ensemble filtering. And in particular, we'll be finding out ways to analyze this method a little bit better and coming up with new family of algorithms. So before I start, I would like to give credit to my co-authors in this talk, Ian Grooms, Mohamad Gharamti, Jeff Anderson, and Ricardo Baptista. So a little bit of background to get this talk started. In the Gaussian anamorphosis approach was first proposed in the seminal paper of Bertino et al. From 2003 as an extension of the standard Gaussian anamorphous EnKF method. And the premise behind this approach was that the model variables that we wish to estimate do not actually need to have standard Gaussian properties, but instead they can be subject to a transformation which will allow them to benefit from the good properties of this distribution. And since then, the method has been applied to a variety of geoscience applications, some of which I have listed down here, and mostly due to the ability of this method to more effectively handle non-Gaussian statistics compared to the more standard particle filter approach. So as you can see here from this equation set, the original GA-EnKF update of Bertino looks exactly the same as the standard EnKF update, only that with the main difference that now we're applying the analysis update to the transformed state and observation variables, which here I have denoted with these tilde symbols. And a couple of notes here on the algorithmic details for the observation anamorphosis function, TY. We typically take a analytical transformation, which is guided by our knowledge of the non-Gaussian likelihood, just like what Javier pointed out in the questions. Whereas for the state anamorphosis, usually it's done in an empirical way and based on a climatology of ensemble forecasts that is centered on the analysis time. And so for the sake of speed, these anamorphosis transformations are also typically univariate, in which we simply have this function composition of the non-Gaussian CDF-F of the variable we're interested in, which is composed with the inverse of the Gaussian CDF, similar to also what Jeff presented in the first talk. So while this algorithm the GA-EnKF algorithm is specifically designed to respect the physical bounds of model variables, a lot of previous studies have identified pathological cases where the performance of GA-EnKF can be actually worse than the benchmark EnKF. And so one example comes from the study from Grooms, 2022, where you can see that this specific variant of the GA-EnKF, which is plotted with the orange curve, has larger RMSE errors than the EnKF for all of the tested ensemble sizes here in the context of the Lorentz 63 model. So clearly understanding the reasons behind these pathological cases is extremely important given the widespread use of these algorithms. So in the first part of this talk, what I'd like to do is to take a little bit of a closer look at the mathematical properties of the algorithm and try to understand where these problems may be coming from. So the first technical problem that we encounter with GA-EnKF method is the sensitivity of the analysis update to the choice of anamorphosis functions. So here, in order to illustrate that, we're looking at a very simple Bayesian example in which we work with a lognormal prior and a lognormal likelihood. And the only difference between the bottom two panels is that the parameters I have chosen for my target Gaussian space. On the left, we have a standard Gaussian, whereas on the right, we have a moment matching Gaussian in which I have matched the mean and the variance of the probit function to be exactly the same as the prior ensemble. And you can see that with the original formulation of the GA-EnKF update, while on the right we recover the exact posterior, which is plotted with the solid black curve here. On the right, we end up with a highly biased analysis ensemble that is shifted to the left of the posterior distribution. So in the same paper that I just quoted, Grooms 2022, Ian introduced a new variant of the Gaussian anamorphosis method. And from the new set of equations that I have written down here, you can see immediately that one of the straightforward benefits of this method is that we no longer need to define observation operator and an error covariance matrix R in this transformed Gaussian space, which in many cases is quite an ambiguous choice to make. Instead, what we need to do is to generate this transformed observation ensemble, which is done by simulating from the likelihood P of y given x, where we simply replace the x to be fixed to each ensemble value, and then we apply the observation anamorphosis function to the resulting sample. So now our first theoretical result comes in here, and we show that with this modified version of the Gaussian anamorphosis approach, the analysis update is actually invariant to the choice of the target Gaussian space. So whatever moments we pick up for the target Gaussian space will end up with exactly the same result. And one of the key steps in proving this result is to realize that every two anamorphosis functions can be related through an affine map. So now if we pick up a simple univariate Gaussian case, the form of this affine map looks just like this. What we've also in the context of the ensemble adjustment command filter is see adjustment of the scaling and adjustment of the mean. So while this invariance property is already a really nice improvement over the original method, it still doesn't tell us much about the accuracy of the anamorphosis approach. And so this is where our second result comes in handy. So in this theorem here, we prove that the modified version of the anamorphosis approach is Bayesian consistent in the special condition where the separate transformations of the state and observation variables produce a jointly Gaussian space. And so in essence, what this result tells us that if we satisfy the condition of joint Gaussianity, this modified GA-EnKF algorithm would be both invariant to the choice of target Gaussian space or anamorphosis functions, but will also give us the correct analysis solution in the limit of an infinite ensemble size. So one setting where the condition of joint Gaussianity is satisfied is if our likelihood takes the special form of a Gaussian distribution that is pushed forward with the inverse of the observation anamorphosis function. And so the lognormal likelihood is just a special case of the statistical model. And indeed, if we go back to our lognormal example, we'll see that now the modified GA-EnKF update does recover the Bayesian posterior in both of these cases. So we both have the invariance property, but we recover the true posterior distribution. Of course, in many cases, the likelihoods do not take the special form that they wrote down on the previous slide. And one example where this is violated is if we take, for example, an inverse gamma likelihood. So now in the second experiment, we're pairing this inverse gamma likelihood with a gamma prior, which is exactly the setting that Craig Bishop considered in 2016 paper for his GA-EnKF update. We see that the modified GA-EnKF update remains invariant in that the analysis histogram is the same between the two plots, but is no longer Bayesian consistent. And in particular, here we observe that we have heavier tails compared to the true posterior distribution. So now the question is, what can we do in order to handle these more general likelihoods that we typically have in data simulation setups? So the approach that we took is to relate the GA-EnKF framework to two approaches that have come up recently in the literature of nonlinear ensemble filtering. The first one is this transport-based data simulation framework that is summarized in the recently published paper of Spontini et al. In SIAM Review. And the second one is the conjugate transform filter that they introduced during the ISDA conference in Fort Collins. So now the commonality between all of these methods is that they share this latent Gaussian structure. And so what I would like to do in the second part of the talk is to exploit this commonality and build a new family of nonlinear ensemble filters that combine specifically these ideas of measure transport and Gaussian anamorphosis. So for those of you who may not be as familiar with measure transport, here is a quick overview slide of what this means. The main object in all measure transport theory is a transport map S, which we say induces a deterministic coupling between a simple reference distribution most typically a standard Gaussian, and a more complicated target distribution here on the bottom that we wish to sample from. So the specific type of transport maps that were considered in this Pantini et al. Paper that I cited a couple of slides ago is called Notte-Rosenblatt rearrangement, or KR for short. And in the special form that they've written down here, you may be already identifying that it has a nice structure, in particular lower triangular structure, in that the kth element of this map only depends on the first kth element of the input vector x. And this lower triangular structure leads to a number of appealing properties that they have summarized here on the bottom. But more importantly for us, how can we use these KR maps in the context of data simulation? So what Pantini et al. Did was to concatenate the observation and state variables into a single vector, and then construct this two-block transformation SY, in which the first block takes the observation variables y, whereas the second block takes the joint state and observation variables. And it turns out that once we've defined this special KR map, then we can come up and derive a Bayesian consistent analysis update, which takes the following form here, in which we have a composition between the second block in the KR map with its partial inverse, where for the first variable, we're fixing it to be equal to the true observation variables YO. And here, just a quick note is that these YFK variables is exactly the observation in sample that we used in the modified version of the GA-EnKF method. So what is interesting though is that the second map, and I'll go back here just to point it out again, the second map in the composition, from a mathematical perspective, it turns out it's not a unique transformation. And this leads to the new developments that I'm going to present here. So it's not a unique function, and actually it can be any function as long as it can transform the original sample to a standard normal sample. And this leads to a number of algorithms that we can develop here, a number of options. The first two options correspond to the original form of the transport map, SY, that I showed earlier. Options 3 and 4 can be derived from an alternative transport map, SX, in which I've simply swapped the order of the state and observation variables and written down here. And then there's this fifth option, which is perhaps the most naive one, in which we simply generate a sample from a standard normal and then apply the partial inverse in order to get back to the analysis posterior. All right, so the question now is, how can we use these insights from measure transport theory and relate them to the Gaussian anamorphosis framework that we talked about in the first half of this presentation? Well, here is where the two-step filtering framework of Anderson 2003 comes in handy. More details on this will be presented in the next talk. Here, I'm just going to outline the key aspects in that the posterior PDF, so sort of relating this two-step filtering framework to the Bayesian formalism, is that we can write down the posterior PDF as this integral expression involving two conditional PDFs. And essentially, the special form of the posterior PDF allows us to develop an analysis scheme that is broken down into two steps. Whereas in the first step, we sample from this observation, in observation space from this second conditional PDF. And in the second step, we regress our observation analysis to the unobserved part of the state by sampling from the first conditional PDF. And so next, I'm going to focus on the first step of the algorithm and show you how we can use the concepts from measure transport in this context. So in particular, this lower dimensional structure of our vector zy, z being the state variable and y being the observation variable, allows us to write the KR map in an exact form using a special form of a two-dimensional Gaussian anamorphosis, which looks like this, where the first component and the second component are now represented again as this composition between a non-Gaussian CDF on the right and the standard Gaussian CDF inverted on the left. With the difference that here in the second line, you can see that instead of a marginal CDF, now we're working with conditional CDFs. And what is the significance of this formulation? The significance is that if we work in high dimensions, the stochastic map filter that I represented before needs to parameterize the transport maps and estimate the parameters behind these maps. Whereas in this lower dimensional setting, the nice thing is that the form here allows us to estimate the non-Gaussian CDFs using readily available tools from the Dart software. So now the 5 analysis options that I showed in high dimensions also simplify very nicely in this lower dimensional setting. And the really nice result that we arrive at is this option 4, in that it simplifies to the rank histogram filter and the quantile conserving ensemble filter that Jeff presented in the first talk. Also we have these additional 4 options, which now generalize the observation space update in the Dart software. So we have a little bit more flexibility in how we can handle non-Gaussian distributions depending on the type of problems we're working with. So what I'm going to do next is to verify the Bayesian consistency of one of the non-RHF, non-QCF algorithms here using the same gamma prior inverse gamma likelihood Bayesian example that we saw in the first part of the talk. So here in this slide, I'm showing you the action of the first component of the KR map. We see that applying this to the prior ensemble members tends to move the prior particles only along the z-axis, such that the final result is obtaining a standard Gaussian distribution in this marginal variable. Whereas in the second animation, we see the action of the second component of the KR map. Here, there are 2 effects happening. The first one is that we obtain a standard Gaussian distribution for the y variable here on the marginal histogram. But also the important thing here is that the effect of the second component is to force all these particles such that we obtain a bivariate standard Gaussian structure as well. So here I'm verifying the Bayesian consistency of the TGA-EnKF analysis update. So you can see here that applying one of the non-RHF schemes does indeed recover the true Bayesian posterior in this gamma inverse gamma example. Unlike the modified version of the GA-EnKF algorithm, where I'll remind you again, we had a biased analysis ensemble. And indeed, here is just to verify that the GA-EnKF algorithm, which is, thank you, which is designed to solve these kind of problems, also recovers the true Bayesian posterior. But the difference is that if we flip back and forth between these 2, we'll realize that they're not exactly the same. And this is because the observation ensembles in them are not sampled from the same distribution. And the other thing is that the new class of algorithms can be fitted to an arbitrary priors and likelihoods. So just to sum up really quickly, in this talk, we analyzed the Bayesian consistency of GA-EnKF and derived a new family of algorithms for the observation space update in Dart. And there are a lot of interesting research to happen in the future. Most importantly, we'll start with verifying the performance of the 5 new updates that I introduced today, specifically by varying ensemble sizes, observation uncertainties, and degrees of nonlinearity. At the end, there is a number of useful references that I encourage you to check out. And with that, I would like to close this talk, and I'll be happy to take your questions. Thank you.
Okay, great. Thank you very much, Hristo. Excellent talk. So I don't think there's any questions yet. I don't see any questions in the Yopad. I'll give it a minute for people to ask any questions. If you have any questions, please use the Yopad in the link provided. Yeah, if there's any people wants to ask a question, please write it down. We especially encourage any questions from like PhD students or early career scientists. If you have any questions, please also write them down. We highly like that. Okay, so we got a question coming through. Let me just. Okay, I think it's from Patrick. Let me just give him some time to write it down. Okay, he says he wonders about the code. Do you have it politely?
Let's see. Oh, so Patrick, do you mean the code is in whether this is freely available in Dart, or whether if that's what do you mean, then okay, that's what you mean. All right, well, Much like what Jeff said in the first presentation, exporting all of these 5 analysis updates in that will be extremely trivial. We have all the necessary tools in order for that to be done. It will be a trivial extension of the readily available rank histogram filter. So yes, it will be nice to be able to compare this performance in a way that doesn't require much coding, and I'm looking forward to checking these results.
Okay. Okay. Patrick says, thank you.
Thanks,
Okay, we have another question from Michael Ying. Do you plan to test the scheme in some higher dimensional systems?
Hi, Michael. Thanks for your question. Yes, I think the interesting part here would be to especially test the validity of different regression. For example, testing much like what Jeff is doing with his algorithms is testing linear regression versus quantile regression versus logistic regression and so on. Theoretically, if you obtain better analysis results in observation space, you should be able to get better analysis for the unobserved part of the state. And so this is sort of the premise behind trying to test these 5 different updates in observation space first before scaling this up to higher dimensional systems. And so yes, I think it will be the next step once we verify for what kind of problems these 5 analysis updates will be more suitable. The next step would be immediately to see how well can they capture also the unobserved part of the state. And so I'll be looking forward to test different types of regressions for different types of problems.
Okay, thank you. Michael says, great. That's exciting.
Thanks, Michael.
Thank you, Michael. Thank you for the questions. Thank you very much, Hristo. I think we should move on to the next speaker. Thank you very much for your talk.
Thank you.